So the next presentation is by Taiwo Omotoso from the University of Oklahoma on the influence of Ruthenium Titania catalyst pretreatment conditions on the upgrading of biomass fast pyrolysis oil vapors.
Good afternoon, ladies and gentlemen. My name is Taiwo Omotoso. I'm from the Department of Chemical Engineering, University of Oklahoma, and I would like to take advantage of this brief time to present on the influence of the pretreatment conditions of a bifunctional catalyst on the upgrading of the vapor products of fast pyrolysis of biomass. The high oxygen content contained in the liquid bio-oil we produce without this catalytic bed here is really implicated in most of the major disadvantages we see from the bio-oil we produce. Therefore, our main objective is to catalytically remove the oxygen moieties from the bio-oil before we condense it into the liquid phase by putting a catalyst bed here, while also fulfilling the twin objectives of minimizing loss of carbon to gaseous products and the deactivation of the catalyst used for the upgrading process. Based on this, our methodology basically involves using a model compound guaiacol, which has two oxygen moieties, and it's a major representation of the phenolic compounds present in the bio-oil product, and to study its deoxygenation over a bifunctional ruthenium and titania catalyst system. And keeping our objectives in mind, we're working with varying the calcination temperature of this catalyst and studying this effect at 400 degrees C calcination and 500 degrees C, and also working with two different kinds of titania support, the low surface area P25, which is a mixture of two morphological phases of titania anatase and rutile, and the high surface area pure anatase support. Our results, which are very interesting, shows that high up here we can see that the catalyst calcine at 400 degrees C is not only far more active than its counterpart calcine at 500 degrees C, but it's also more selective to the production of aromatic hydrocarbons, which reflects complete hydrodeoxygenation. And we can envision that when we calcine at 400 degrees C, we have a higher presence of the metal particles on the surface of the catalyst, and while we can think that on the 500 degrees C, due to possible metal support interactions, we have a sort of covering on this of the metal by the support. And also very interesting, also we see that using the low surface area P25 titania, we see deactivation as we go on time on stream. We are following the conversion of guaiacol. We see deactivation while supporting the metal on pure anatase. We have a stable catalyst here, and also a catalyst which is more selective to aromatic hydrocarbons production. And we think that on this low surface area titania, we are forming larger metal particles which could be more susceptible to coking, and hence the deactivation we see here. Based on this, we can conclude that the bifunctional ruthenium titania system is an active and stable catalyst for deoxygenation under atmospheric pressure of hydrogen, and also the calcination temperature, as we've seen, plays a very important role in not only the activity but also the selectivity of this catalyst for upgrading. And last, we see that the nature of the titania support we use also has an effect on the stability of the catalyst and the product selectivity. I want to say thank you to EPSCoR for the funding for this project, and thank you for listening.